As we wrap up Chapter 8 here with Section 8.6 exponential decay functions, we're going to build off of the previous video of exponential growth functions. This section really should be pretty straightforward because it's very closely related to what we did yesterday. So a quick reminder, or review I should say, this is the exponential growth function where y equals a times b to the x power, where a has to be greater than 0 and b has to be bigger than 1. Okay, a is greater than 0 and b is bigger than 1. If a was less than 0, then remember that's a reflection. We can have things where a is less than 0, but as long as a is not equal to 0, we're fine here. Okay. So exponential decay just goes the other way. So let me just show you again. So here's growth. We're getting, as x gets bigger, whoops, sorry about that. As x gets bigger, y starts to increase rapidly. Okay, and that's an exponential growth function. Exponential decay means you're going away, you're decomposing, and so now as x gets bigger, y decreases. Okay, and so again, it's pretty much just going the other way. All right, so here's the thing about an exponential decay function. You'll notice this guy in here that you're raising to a power, that you're raising to x, is going to be less than 1. Okay, so it says graph the function y equals 1/2 x, identify the domain and range. So here's what an exponential decay function is going to look like as far as graphing. When you plug in -2 for x, okay, I don't have a ton of room here, so I get y equals 1/2 to the -2. Well, the -2 flips things inside, so really it's just 2 to the second, which is 4. So this is 4. If it were -1, you'd have y equals 1/2 to the -1, just flip the things inside, you end up with 2. Anything to the 0 is 1. Raise it to the 1, you're going to get 1/2, and raise it to the 2, you're going to get 1/4. So at -2, you're up at 4. Okay? At -1, you're at 2. At 0, you're at 1. At 1, you're at 1/2, and then you're at 1/4. Okay, and so your exponential decay function is going to look something like this, the graph. Domain, okay, again, that's x values, what x values get hit, so we're looking here, and just think, vertical lines. Are there any vertical lines that you could ever draw that are not going to get hit? And the answer is no. Therefore, the domain, all x values work, all real numbers. The range, however, when I look at my graph with respect to the y-axis, when I start drawing horizontal lines, clearly that green one I just drew here does not get hit. Neither does this one. Neither does this one. Neither does this one. We don't actually start getting hit. This one won't even get hit. Okay, but as soon as I go a little bit above that 0, I end up starting to hit my graph. And I'll hit my graph from this point all the way up. Okay, and so your range is all y values greater than this y value here. Well, the y value at the x-axis is 0. So the range, the y is greater than 0. Domain and range is something that a lot of students struggle with. So just be patient with it and keep working through it. So, okay, in the previous slide, we already did y equals 1/2 to the x. And so I'm going to go ahead and just fill in this table real quick. So this was 4, this was 2, this was 1, this was 1/2, and this was 1/4. All right, so I'll graph that real quick. So -2, 4, 2, 1/2, quarter, something like this. And then the other one, okay, we're multiplying everything by -2, so I'm just going to multiply this whole column by -2. So it becomes -8, becomes -4, -2, -1, and -1/2. So when x is -2, y is -8. Well, that's going to be off my graph. I only go down 5, so -8 would be somewhere way down here. Okay? And then -1, -4, -1, -4. At 0, we're at -2. At 1, we're at -1, and then at 2, we're at -1/2. And so this guy's going to look something like this. Okay. And we talked about this yesterday too, so this shouldn't be anything too crazy. All right. So what you'll notice here is that the graph of y equals -2x times 1/2 x is a vertical stretch. In other words, if you look at the red graph as it compares to the blue one, the red one is more steep. Okay, it gets steeper quicker than the blue one does. The blue one's a little bit more flat, so that makes it a stretch. And it's a reflection in the x-axis. In other words, if you take the blue one and flip it over the x-axis, you'd end up on the same side as the red one. Okay, so that's what we're looking at here. Let me just back up a step here and just review this real quick too. So remember, what you're looking at for stretch and reflection is the A value. If the A value is negative, got to be a reflection. If the A value is bigger than 1, which 2 is bigger than 1, it's a stretch. If this 2 were less than 1, in other words, it was like 1/2 or 1/4, then it would be a shrink, where it would be a lot flatter, okay, or a lot wider. So example 3, that's all we're working on, is identifying exponential growth versus exponential decay. This really is not a difficult concept once you understand what you're looking at. The thing that determines whether or not it's growth or decay is the guy inside, the guy that we're raising the x to, or the exponent to, okay? If that thing is bigger than 1, it's growth. If it's less than 1, it's decay. Well, 4 is bigger than 1, so this is growth. Okay? Part B, 0.75 is less than 1, that's a decay function. Part C, less than 1, right? 2/7 is less than 1, that's decay. Part D, 5 is bigger than 1, that's growth. That's all you're doing when you're looking for growth versus decay. Look at your B value. Okay, example 4 says tell whether the table represents an exponential function. If so, write a rule. So remember, for an exponential, the thing that you're looking for is for each consecutive x, which these are all consecutive, so that makes life easy, is there a constant multiplier? Okay, and the answer here is, right, to go from here to here, you're dividing by 10, but dividing by 10 is the same thing as timesing by 1/10. To go from 10 to 1, times by 1/10. To go from 1 to 1/10, times by 1/10. So this one is yes, it is. Recall, exponential functions are y equals ab to the x. In this case, your a, when x is 0, y was 1, so your a is 1, and your b is this multiplier, 1/10 to the x. So really, we could simplify this down one more step and just say y equals 1/10 to the x power is the function. Okay. Part B, and again, that would be an exponential decay function because that's less than 1. And there's no stretch, shrink, or reflection here because the a is just 1. So we're not doing anything to it. Okay, it's just your standard decay function. In part B, again, we're consecutive here, so that's good. We recognize that. And then you say to go from here to here, that's times 4. From here to here, times 4. Here to here, times 4. Check. That is an exponential as well. Y equals a times b to the x. The a, remember, when x is 0, what's y? It's 8. What's your b? The multiplier. There's your function. It's a growth function because the 4 is bigger than 1, okay? And it would be a stretch because 8 is bigger than 1 as well, okay? If it was a negative 8, it would also be a reflection, but clearly it's not negative. Okay, just like we talked about yesterday, or in the previous video, I should say, we talked about an exponential growth model. Here's your exponential decay model, okay? A is the initial amount, just like it was. R is the decay rate. T is the time in years, and R is the decay factor. So example 5 says the population of a city decreased. That decreased is a key word there. The population of a city decreased from 1995 to 2003 by 1.5% annually. In 1995, there were about 357,000 people living in the city. Write a function that models the city's population since 1995. So it's decay, right? So we're y equals a times 1 minus r to the t. So in this case, y equals, the initial amount was 357,000. That's how many we started with. The decay rate is 1.5%, so it's 0.015 to the t. And we should go one more step here and say y equals 357,000 times 1 minus 0.015 should be 0.985 to the t. And again, you notice the thing being raised to the exponent is less than 1. That's what makes it a decay function or model. Okay. Part B says find the population in 2003. Well, from 95 to 2003, that's 8 years. So what that tells you is plug in 8 for t. So 357,000 times 0.985 to the 8th power. Okay, and at this point, this is where you'd have to have a calculator. And so we go to the calculator, we plug in 357,000 times 0.985 raised to the 8th power, and we get the population to be roughly 316,343 people. Okay. So in 8 years, you've lost almost 40,000 people. Actually, you've lost over 40,000 people. Example 6, a farmer bought a tractor in 1999 for $30,000. The value of the tractor has been decreasing at a rate of 18% per year. Write a function that models the value of the tractor over time. So again, it's a decay model. So y equals initial, so 30,000, times, you're decreasing at a rate of 18%. That's 1 minus 0.18 to the t. So in other words, y equals 30,000, and then this will be 0.82 to the t. Part B says, what's the value of the tractor in 2005? Well, it's been 6 years. Okay, so in other words, plug in 6 for t. Y equals 30,000 times 0.82 to the 6th. And then at that point, that's when you would go to your calculator. 30,000 times 0.82 raised to the 6th. And you get the tractor's worth roughly $9,120.20. All right. So in 6 years, you've lost quite a lot of money, over $20,000. And again, this is a model that a lot of people, this discussion comes up a lot when people determine whether or not they're going to buy or lease a car, because one of the arguments against buying a vehicle is that as soon as you drive it off the lot, you're losing money. Okay, immediately you lose money on it. And so these are actually models that are quite common in the real context of the real world, so to speak. So anyway, so this whole section here on exponential decay, hopefully you understand what a decay model is, a function is, and then also how to identify growth versus decay. And again, if there are any questions and you're still a little bit hazy on any of these ideas, as always, just make note of it, bring it to class, and hopefully we'll clear things up then.